In the previous video, we saw that we developed a naive function called is prime, which will tell us if the number being supplied is a prime or not a prime. The logic was quite simple. We just looked at every number between 2 and n minus 1 and see if there's a divisibility. So the question to ask ourselves is this efficient? One way to think about it is, okay, look, let us try to find out how many operations are actually done in running this algorithm. In fact, the answer depends on the value of n. For example, for every even number. So, if I give a number which is a multiple of 2, you realize that in fact we just make one pass through the loop, no matter how large the number might be. The number might be, let's say, 40 digits long or 100 digits long, doesn't really matter, because remember this break statement, you know, all I'm going to find is this, the moment I run this with 2, kk being 2, remember this is a for loop, so kk takes on the value 2. The moment I find this condition, I immediately break out. So for even numbers, it's in fact very efficient. No matter how large the number is, in just one, let's say, iteration, I get out. So one pass of the for loop, I'm out of the function, and I know this number is not a prime. So quite good. And that's why this break here is important, because if I didn't do this, then I'm just going to be basically running this for longer, which is not needed. Similarly, all multiples of 3, in fact, will require 2 passes through the loop for the exact same reason, because 2, is not a multiple. For example, odd numbers, which are multiples of 3, say 21, I just run the loop 2 times. So not bad, right? But the question is, what happens with a prime number? Which means that if I actually supply a prime number to this, what happens, and how many loops, how many, let's say, iterations through I run through this, right? Well, think about it. If it's a prime number, this condition is never going to happen. Result equals to false, which means this break will not come into play. What that means is that I'm going to run this 2, 3, 4, 5 until n minus 1. What that means is that basically we'll go through the loop almost n times, right? So it's kind of like the larger the n is, I'm going to run through the loop many more times, right? So in other words, basically, you can say that the computing load is increasing linearly with n, because it's a function of n, right? So when we say linearly, it's like a function of n. There's no n square term. There's no, let's say, other function of n that is involved. So it's directly proportional to n. And this is very clear because, like we said, right, if the prime number, the break doesn't come into picture at all. But then you might say, okay, so what's the big deal? How does it matter, right? How can I really feel it, right? One way to feel this is to look at the runtime of this, but with a lot of caveats. What we will do is, we'll see how long does it take to run. Like, for example, how many seconds it takes to do the computation. But I must highlight that this is quite tricky, because amongst the runtime itself depends on many factors than just the algorithm itself, right? So, I mean, first and foremost being, let's say, the speed of the computer that you're looking at, the memory you have available, the style of writing code, the language that you're looking at, and so on. A higher level language like Python will take longer compared to, say, a lower level language like C, right? So there are many factors that are going on. But still, even though runtime is not, let's say, a very watertight, let's say, mechanism to establish complexity, it in fact provides us great amount of intuition, which is why we are going to look at it. Even though, like I said, a clearer view always comes from asking the question, um, how many operations my, let's say, my algorithm is doing. And remember the question, is my algorithm doing more work than what's actually needed, right? But never mind, we can still write the, let's say, write the code in a way and log the time that it takes. So I get back here to my code, and I, basically just ask, I want to just find out how long it takes to run, let's say, this computation. So I go and import time. And all I'm going to do is to kind of define two instances of time, one before calling the function and two after calling the function. And I'm going to print the difference between the two. So I just go and say t naught, for example, is time dot time. That's basically saying that the time right now. Remember, I'm calling the t naught as a time instance, like a snapshot of time before I call the isPrime function. You can also use dt.datetime.now, because datetime will do the same exact thing, current time. So I find the time, let's say, before calling the function. I let the function be called, and thereafter I call this once again is, let's say, time.time once again. So now remember, t0 and t1 are both snapshots of time, in whatever units. But I can, what I'm interested in, let's say, is the difference between the two. So how long did it take to run the code? So I can just go and say R for, say, result. I can print both R and T1 minus T0. Now, mind you, this is not going to be a very precise measurement, but still some very interesting insights are going to come through this. Let's say we call this function for different number of primes, right? So we're going to call it for small primes and then progressively larger primes and see what happens, right? So let's say I call this function for 11, which is a prime number. So, obviously 11 is a prime number. When I, let's say, run this piece of code, when I run this, it tells me this took very small time. So 9 times 10 to the power minus 5, right? Which is, now if I run it again and again, you realize that there is some difference. That's okay, but you're getting the idea of the scale, that it's of the order of 0.0001. In fact, this is reasonable. It took a very short amount of time, and it's quite impressive, I would say, right? Um, let's say I make the number larger. That was a two-digit number. Now I run it for say 1009. Now remember, as I'm increasing the number of digits in the number, basically the number of times the loop runs also increases. So this time round, I'm going to run approximately 100 times longer, 100 times more operations through the loop, approximately 100 times more passes through the loop for 1009. When I do this, doesn't seem to matter much, right? In fact, I get still the same 0.001. Of course, I can run it a few times. This is never going to be exactly the same all the time because, like I said, this depends on multiple factors, but some insights are going to come through this, right? So let's make this even larger. Now, 1009 is a prime. For the small, let's say I run this for the smallest six-digit prime, that's 100003. When I run this, it's probably similar, not little bit long perhaps, but not so clear, right? It's like maybe borderline. All right, so let's say I increase this further and I go to 15019. Now this is an eight-digit number. Obviously, like I said, the number of passes through the loop is increasing linearly, so we expect this to start taking longer. And indeed, you can feel it. Even though the first few times it did not really seem to matter much, but now clearly the running time has gone into zero point 0.6 seconds. Remember, it was starting with something like 0.001, right? Something like that, but now it's 0.66. Now, I must highlight that when you run this at your machine, and at your time, perhaps the numbers will not be the same. That's okay because there are multiple factors that are determining this, but the trend is unmistakable, and that's what I'm going after. Notice this has become 0.66. Let's push this even further. Let's say I go to a number which is a 10-digit prime number, which is, let's say, this quite a large number. Now is when you really see something's happening. This is working. Now you can see this is taking time. In fact, this is going to take a really, really long time. Now, why is this happening, right? Think about it. When I go from an 8-digit number to a 10-digit number, it's kind of multiplying that number by 100. Kind of, not exactly, but kind of, right? Obviously, it's a prime number, so it's not true, but approximately multiplying by 100, which means that if it took me zero point 0.6 seconds to run for an 8-digit number, reasonably so, I can expect that this is going to take in the order of, let's say, 60 to 65 seconds to run for a 10-digit number. Now, this is where I said the intuition that comes while looking at these run times is unmistakable. It's amazing. We are still running this function. It's 53 seconds already. Like I said, it may be a little bit faster for you. It may be a little bit slower, but the difference between an 8-digit number to a 10-digit number will be noticeable. Perhaps for an even faster computer, you might say, okay, look, 10-digit number also runs quite fast, but then you can try, let's say, 20-digit number to a 22-digit number. The difference will be felt always, right? There'll be a point where this will take way too long. Notice this took 75 seconds. 75 seconds from, let's say, 0.7 seconds. And that's kind of consistent because this algorithm is running that much longer, right? So if I were to, so let's summarize this, right? So I've done this previously. Like I said, the numbers may not be exactly what I got now. That doesn't really matter, but the trend and the insights that we are getting from this are really, really interesting. So I have here the number itself, n, say the number of digits in that and the time it took. So if you notice, going from two-digit number to a six-digit number really did not change things. Now the way to understand this is that for this size numbers, there were other steps in the whole execution that dominated. But then as we make the number larger, for example, here an 8-digit number or a 10-digit number, clearly our algorithm starts to dominate. You can very clearly see that, there's a linear dependence on n. As I go from 8 to 10 digits, like I said, it's kind of approximately multiplying by 100, and this is exactly what I'm seeing. So very, very clearly, it's now our algorithm that is starting to dominate. This is becoming quite slow for a experience. I mean, 10 digits is not much for a prime number. Much larger prime numbers are known. Now, if I were to test those for primarily with my function, this number is going to go very, very large, right? So clearly something needs to be done. So even though runtime is let's say an imprecise measure, still gives us pretty good insight, right? Um, so the observation that we are making is that, look, this was a naive algorithm. We knew that all the while. It looked okay for small numbers, but the moment I start making the numbers large, for example, if I look at the smallest 10-digit prime number, which is what I did, it took more than a minute on our machine. Actually, it's on the Google Colab, let's say, machines. And you can see that if I were to go the largest 10-digit prime, this is going to be 10 times more than the smallest 10-digit prime, again, approximately speaking. This is going to take at least 10 to 12 minutes. So that is way too long for an action like this. Also, the question is not so much about the time taken. Some things will take time, but the question is more about, is my algorithm doing more than what it needs to do? In fact, it is. As we'll see, a simple but clever twist to our algorithm will bring this running time down drastically and increase the efficiency of the whole thing. That is for another. Why-byte Algorithms and Olympiad track is for people who are interested in understanding algorithms deeply. Look at our website www.ybyte.in for more details. Forever enjoy coding. Take care. Thank you so much. Bye bye.